So now we saw that this describing function is certainly something valuable to look at nonlinear features. And then we decided to look at a little more complicated systems. So for example, by placing these flames inside a chamber, and this is work done by Frédéric Boudy, who is now working for Alstom or General Electric. And so again, the idea is that we want to understand loops of that kind. We are interested in the limit cycles. We know that there is this very general framework where we project on the modes. We've looked at the combustion dynamics, and we've seen how to represent things of that kind using a transfer function. In general, the acoustics in the systems are treated linearly. In fact, there are nonlinear features. Somebody at the beginning was asking, when you go to very high level of acoustics, isn't it necessary to account for nonlinear acoustics? Yes, probably, and there is work in that area. But what is most nonlinear is combustion. Combustion is much more nonlinear than acoustics. So, in fact, this is of order 1. You know, the fluctuations in heat release can be very large, while the fluctuations in pressure are perhaps not as large. And so the idea was to treat the nonlinearity by actually considering a family of describing function. Now, with respect to previous work in this field, while there is, for example, the work of Anne Dowling, but this was purely theoretical. There was no comparison with experiments. So the first comparison with experiments is what we've done with Nicolas Noiret. What you've seen in the previous slides is exactly the first, to my knowledge, a good comparison between theory and experiment, where you definitely see that you can calculate limit cycles, that you can represent switching, that you can represent triggering. All that doesn't exist in the literature before. Just to say, when I say that, it's because in some papers we are not even cited, and people use the flame describing function. It's incredible. So anyway, so the objective is to actually provide the modeling elements to look at that, develop nonlinear stability analysis, show how to anticipate nonlinear phenomena, and analyze also the limitations of this framework, because it cannot cover everything. You have such a variety of possibilities that certainly this is good up to a certain point, and of course, then you have to find something better. So the experimental configuration, and then we will look at linear stability, nonlinear stability, and the results of nonlinear modeling. But this time, you see the device has this additional feature. You have a tube here. So it looks like a real combustor. Manifold, upstream manifold. You can change the length of your combustor. You can change the length of the manifold. And you have the flames here. You can even change the sizes of the flames. And you can play with the describing function of this perforated plate. So by changing the size of the orifices and so on, you can change this FDF. So for example, here you have the perforated plate. This is the piston where you inject the combustible mixture. This is a top view. You see you have 420 holes here. This is the device. You have a photomultiplier, microphone. We set also a microphone at the back of the chamber here. You have a hot wire inside, so you can actually track the velocity fluctuations. you can put microphones on the upstream, so you can actually, 2 microphones allow you to determine the velocity, the acoustic velocity. So that's useful. We know that the velocities in these channels are important. And this is typically the limit cycles that I was describing. We've seen that the flames execute this motion. All of the flames at once move up and then move down, and there is shedding of a pulse. This is a cyclic oscillation at this frequency, for example. We've seen this film already. You have stable combustion in a very narrow region. In some cases, you don't even have stable combustion. The system is unstable for all lengths. It's nice to have at least a region where you are stable. Well, that doesn't work. So, so what happens now when we have this combustor? Well, the behavior is somewhat the same. You see here a very high level of sound developing, so the system is pretty loud. This region is stable. You still have noise because it's flow noise, and this noise is pretty strong because the jets flow through this perforated plate. And then you see that the frequency first is aligned with this quarter wave mode and then goes to this 3/4 wave mode here. And this is microphone M1, so you can see the microphone M1. It's outside this combustor, but still the noise level is high here, whatever the lengths, except in this region where there is a stability. So this is unstable, it's stable. This is again unstable here, it's a different mode. As you change the size of the combustor, you see that the difference between the mode, the acoustic modes that you can calculate, the frequencies of the acoustic modes that you can calculate, and the frequencies that you measure, the differences become larger. You see here it's larger, and here it's even larger. Yeah. And here you see that there is no more stability. In this case, when your combustor is too long, essentially everything it's all the time unstable in this particular situation. It's very weakly damped, so there is very little damping in the system, so the system is unstable everywhere. Here you still have some stability, but here you don't. Now, there are 3 types of analysis that you can carry. First of all, you do an acoustic analysis. This is just considering acoustics, taking into account the fact that on one side the temperature is higher than on the other side. And so you assume that. You take also into account the fact that the area has changed. And you do an acoustic analysis. This gives you a dispersion relation, and you get the mode structures, but you don't have any information on unstable modes. Then you take a transfer function. You assume that you have a transfer function. In this case, you obtain a dispersion relation which depends on omega, but you don't have information on the limit cycle. And then you assume that this transfer function depends on the level of the input, and this gives you the limit cycle amplitudes, the frequency shift during the development of this limit cycle, hysteresis, mode switching, triggering. So by doing that, you get all these rich physics which come into the picture. And so to do the acoustic analysis, you use what we explained at the first lecture. You have a duct here and another duct right here. There is a change in area. You change the density and the velocity of sound, the speed of sound. and you connect the two by the area change, and you have a system which is homogeneous, and so you can find the roots of this system. You impose at that point matching conditions of pressure and volumetric flow, acoustics, and plus the boundary conditions. So here it's an open boundary condition, here it's a closed boundary condition, it's the piston. And so this allows you to calculate these modes. But then when you do the measurements, you see that you're here. So there is a distance between the modes and what you actually obtain. This is because the frequency is modified by combustion. It's you are not exactly on the modal frequencies just because combustion gets into the picture and the equation contains that feature. So the second is to do linear stability analysis. So you take a gain like that, a phase which looks like that. You have this initial, you know the modes. So this is very useful because you can start the search of the roots of the dispersion relation from the modal frequencies, and you do that by continuation. You begin with what you know are roots, and then you produce an algorithm which will actually bring you to the values that you have. So this is how you get this new roots. It's good to do continuation here. And of course, if this is positive, it's a growing thing. How do you determine this? It's just by placing a loudspeaker. You have this grid. You confine it a little bit just to be under the same conditions, and you can actually have a gain, and you have the phase, which looks like that. And so it's quite important. So you can see that by simply changing the size of the orifices, you change the transfer function. You see this gain is here, it's now here. You see that the phase is growing like that, it's growing like that here. So by shaping the transfer function, you can work on your stability, on the dynamics, just tailoring the transfer function. And by using this linear stability, you get, so you do get, this is essentially what you find in the experiment. So these are unstable points. So the experiments are here. Here you have experiments for actually the two sizes. You see the hole is 1 millimeter here, it's 1.5. You see that things change. For example, for this 1.5, this stability is much larger here. The level is in fact a little lower. You find that the points where the system is unstable for the 1.5 are here and here, while for the 1, they are here. So they are close to the modes that you are calculating. These modes, of course, depend on the lengths. You see the quarter wave, 3/4 wave, 5/4 wave, 7/4 wave. And for example, the 7/4 you can get with this 1.5. And the main difference between the two is that the phase is very, very different in the two cases. For 1, it's here. For 1.5, it's here. And so you predict boundaries. It is possible to show that the first band of instability is between pi and 2 pi here. And so the predicted unstable boundary for a hole of 1 millimeter is this one. So basically all the points, the black points, do fall in this region. Now if you take the 1.5, the bands of instability are this one, I think. And indeed, these points fall closely in here. And then there is another band, which is here. And these points fall there. But you see that there is a difference. You over-predict the regions where the instability will occur. But it's already good. So already this linear stability gives you a fair description of what goes on. It's already a good thing. But of course, when you do the nonlinear, that is, you use the changes in the gain and in the phase, then you're accessing the possibility, whoops, I don't know why. You access the so you see here, so by doing that, you augment your view of the problem to a large extent, because you now access the limit cycles, the switching phenomena, triggering, and the hysteresis. You can explain all that, which is much stronger than what you can do with linear analysis. Linear analysis, for example, doesn't allow you to do triggering. You cannot deduce triggering from linear analysis. So, this describing function was used, for example, by Anne Dowling. She was doing calculations of a flame in a duct. It's a ducted flame. This is the flame holder. This is a purely theoretical calculation of the dynamics of that flame. And you see the flame acts there is a saturation of the heat release fluctuation for that flame. And by using this saturation and using this concept of describing function, you can actually represent some of the mechanisms here. But there is no comparison with the experiment. And here in Noiret and in the Journal of Fluid Mechanics, we do have a comparison. It's not perfect, but it's quite nice. It's already, we were very happy with that. Actually, we predicted things and then went to the lab and found that what we predicted was there. So the lab is 50 meters from the computers. So that was very easy, but it was wonderful. So, and so the difference here it's just doesn't depend on the amplitude. Here it depends on the amplitude. And you see, there are dependencies. And not only the gain, but the phase depends on the amplitude. So, and how do you cope with that? Well, you start with a value at 0. These are the normal modes. And then you increase the value of u prime 1 and increase it and increase it. And so you do continuation here, and you can obtain these trajectories. So the trajectories tell you the story. And so, for example, you get mode 1 here. These are trajectories which are like that. And then you are here. This is a case where you are negative. So in this case, this is stable here. But if you jump to that point, it becomes unstable. And then you have mode 2, which is shown here. This is now with a combustor. And what you can predict is you go like that. You have also the second mode, which you will access. Then the third mode here. The second mode, I'm sorry. And then you have the third mode, which is embedded here if you go a little further. And so what you see first is you travel on that. So this is the initial mode that comes in. And then you jump to this point where it's stable. So you don't see that mode here. And then you move on this frequency. You get to this second mode, and you go here. And if you do it the other way, That is, you go from here, you get here, like here, and then you're stable, more or less. Whoops, again, it's, I don't know. All right, anyway, that was essentially what I wanted to tell you about this. Well, there are other things, but okay, we have to move. So let's move now to the passive and active and dynamic methods of yeah, here it is. Let's begin with this one. So one objective is, of course, to reduce oscillations, to be able to reduce this level of oscillations. And so the idea, you see in the last example, all the flames were moving at once. All these flames were executing the same motion, and the idea was actually to try to modify that. And the idea here is now explained. So, in fact, when you so it's based on a paper that we gave in Montreal. It's the 2008 symposium, and we won the silver medal for that. So it was considered as a nice paper. So the idea is the following: how would you do passive control, no active control? I'll tell you about active control afterwards. Through modification of the flame dynamics. So the idea is is it possible to modify the flame dynamics so that the flames are less sensitive to oscillations? And again, we have this resonant coupling between flames and burner acoustics. Consequences can be very detrimental: structural vibrations, heat fluxes, flame extinction. And solutions: possibly active control, but this is difficult to implement. Passive control using Helmholtz resonators or quarter wave tubes or acoustic liners. But then there is another idea. The idea is, you see the point, if you look at the balance of acoustic energy within the system, this is the gain and this is the losses. And suppose you have just a mode which can come in here. So this is the response of the combustor. And you have the gain, which can be larger than the losses, then you can have instability. So acoustic energy balance is positive and potential thermoacoustic coupling. So first strategy, modify the losses, put Helmholtz resonator, perforated screens. There are systems which are biased flow perforated plates, which have a very strong damping capacity. Difficult to arrange, but a good damping capacity. So there are various possibilities here. But the other so one way is to enhance the losses. The second strategy is to modify the gain by acting on the flame dynamics. So what is the experimental configuration? It's this one. So we have all these flames which are running here, and we've seen that they are all like soldiers in a parade. And we've scanned the various lengths, and we've seen that under certain conditions, this is stable. And if you change the length slightly, it becomes unstable. Of course, you don't want that. So we want to modify this behavior. So the oscillation cycle is this one. We've seen that. So we want to modify that. And as I told you, this is unstable here, unstable here. There is just a small stability here. So of course, what you can do is put more damping. But the other way is try to modify the dynamics of the flames. And yeah, we've seen this, this type of behavior here. Make use of the multiple flame configuration and try to avoid the coherent response of the flames to acoustic perturbations. So we actually got a patent for that. So when you want to patent, you patent a system, and the system is to, in fact, you see, the acoustic wavelengths are very large compared to the flame dimensions. So it's very hard to do something on the acoustics. But if you can go from the acoustics into a convective mode, and then the convective mode has a wavelength which is much smaller because the velocities are much smaller, then you can play with the phasing of the system and transform the acoustic perturbations which impinge the flames to hydrodynamic perturbations, vortices which propagate at the mean velocity much lower than the speed of sound. And so the system is here. It's very simple. You put a diaphragm here and another one here, and you place the diaphragm at a certain distance from one to the other. So you have all the flames here, and so here the vortices are shed from this diaphragm as you have these acoustic waves coming in, and the phase is governed by this distance. So like that, you can change the phase, and if you tailor that for a given mode, it is possible to have a phase opposition, perturbations which will be in phase opposition with respect to the flame. So this is the idea. You shed coherent vortices here, and the flames will act like this. This one will be shorter, while this one will be larger, and then the other situation will be obtained. So the idea is just to place these these diaphragms in all these orifices and move them one with respect to the other in a good position. What is good, you will see. So like that, you don't have this coherent vortex shedding, which produces this motion of all these flames. And so the phase is governed by 2 pi f delta L over the convection velocity here. So you have to study the convection velocity so you can actually separate these two diaphragms here. And we actually verified that this principle works in a non-reactive system. You just place a tube here, and you have a loudspeaker at the bottom. You force the flow, and you put a diaphragm, and you can see the vortices shed by the diaphragm. And here you see a laser Doppler setup just to see the velocity. So the principle is just to place the diaphragm, and you transform the pressure wave into a vorticity wave, partially. And you can see these vortices. This is you see these are vortices shed by the diaphragm as you place acoustic waves. So this is actually one way, in fact, to reduce the level of the acoustic wave is by having a diaphragm, because part of the energy goes into the vorticity. And we've done numerical calculations as well using AVBP, you see, and you definitely, so here what you see is vortex rings. What is plotted is the Q index. So it shows you the vortices that are shed from this diaphragm as you impinge on, as you have incident acoustic waves. This work was done by Nicolas Noiret. He has, and so here you can definitely see that you have something which is convective, because when you plot the phase with respect to the distance, it has a convective shape. You have a certain slope here, and it's indicative of the fact that you have convection. So now we have the another thing is to do the calculations not only on a single flame, but on two flames. So these are the channels. You have the diaphragms here. This shows a little bit of the gridding required, because these are thin flames, so you need very fine grids to calculate these flames. And this is what you get in 3 dimensions. So you have the two flames are moving while vorticity is being shed at the bottom, and you see that they are moving in opposite directions. You can see also the velocity field plotted here. And you can see that even better in this here. So now we call that a dynamic phase converter, because you convert the phase, it's dynamic, it's nicer, and now you have these flames moving in opposite directions, and so you can try to see if it's operational. So in this case, what we do is we excite. This is a case where we place this system inside the perforated plate, and we excite here at a given frequency. And what is seen is that that indeed you have. This is on design. What is obtained here is the velocity at for two flames. So you see one is moving like that, while the other one is moving the other way. And even under off design, even when you are not at the perfect frequency, which is shown here, you have an opposite motion. So the flames, some flames will do something while the others do the opposite. And these are films which show that in practice. And here the flames are moving just like that, but the film doesn't work for some reason. While here, the film, the thing is moving up and down like that. So definitely what was calculated is indeed what is observed. And now you take the chemiluminescence in the classical case without the DPC. This is what you inject, and this is what you see in terms of chemiluminescence. So all the flames have the same heat release fluctuation at the same time. While in this case, you put in the loudspeaker, operates, and now what you get is essentially a constant signal, despite these oscillations, because some flames are going up while the others are going down, so they compensate. So in this case, we are able to compensate the motion, and the flames, this set of flames, becomes essentially insensitive to the perturbations. And then we looked at this DPC device installed in the system. So this is classical injector, is triangles, and the injector including constrictions at the same axial level, not staggered. So these two will generally give the same answer. You will see the same. And when the point is like that, it's dynamic phase converter. So this is the level, the SPL, and these are the frequencies observed. And when we put the dynamic phase converter, we are here. So you see we bring the level down. Still there is a frequency coming in. So we cope with some of the modes, but a higher mode can occur. So you have to damp that as well. But nevertheless, the level is lower. And and here if there is no staggering of these constrictions, you see that the response is the same here. The diaphragm is here, so basically the response is about the same. But with the DPC, it's lower. So it's simple sizing method, low requirement in terms of space and mass, because it's just diaphragms that you include in this perforated plate. Minor modification of the injection system and broadband effectiveness. Drawbacks, a trade-off between additional head losses. There is a little bit of head loss. Eigenmodes far from the nominal frequency may arise. So there is no solution which is perfect, because this is how everything is. There are always a drawback, but nevertheless, it's something. New passive control strategy. A phase converter was successfully tested numerically, experimentally under forced flow conditions without forcing. Do you have any questions here? Yeah.
Did you also try changing the various sizes of the orifices as well?
Yeah, did you try changing the sizes of the orifices? The principle, I think, is working for the different orifices. But of course, every time you have to do a new mechanical perforated plate and so on, and at a point you get bored by that. So you don't do all the systematics, but the principle, what you want is to really demonstrate the principle. A lot of people put patents without even demonstrating anything. So here, we wrote a patent while we had clear demonstration that it was working. So that was but of course, we didn't do all the parametric studies. And in France, a thesis is 3 years. After 3 years, you have to be done. So we need very, very clever students. You see, for example, Nicolas Noiret, he did numerical work, the AVBP calculations, experiments, the FDF, and also this invention, this innovation, and all that in 3 years, and you're done. So, but after the 3 years, it's a new topic, and so there is a strong constraint in France. The thesis has to be a finite time. And so after that, you don't have support. Support vanishes. So this is why we didn't do all the systematics that could be done. And then we had other problems to look at, like, for example, looking at the manifold with a combustor and so on. Yes?
Sorry, I'm not sure I quite got the point across, but you showed two different plates which had different size holes.
Oh.
Plate function was different. So
yes.
Why a plate with multiple different kinds of holes?
Yes. Yeah, that's an idea that we also explored. If you could you, for example, place small holes, big holes, and have something which would be better than having the same holes everywhere. But then you have an inhomogeneity in the flames. You see, the flames are not quite the same size. So we played with that idea. We did experiments on that. This is much better. The DPC, the idea of the DPC is to take the perturbation, transform it into a convective wave, and play with a convective wave, and like that you modify the motion of the flames. Yeah. Anything else? Yes. Yeah.
So for this experiment, my first question is that the simulation that you showed, it showed two subsequent
neighboring flames.
Yeah, neighboring flames.
They were both calculated so that you could see under the same perturbations, the two flames were executing opposite motions. Yes.
Okay, but when you had it in a plate, then there are 6 neighboring
Oh yes.
channels.
Yes.
How was it done in the experiment?
No, but then you are limited by the amount of gridding that is required to do 6 flames or even more. So at a point, at that time, the resources were just to do the 2 flames. We could not do, because here you have a very fine grid. I didn't give the details, but it was already pretty large. It was, and the flame is well resolved, and everything is like in an experiment. So you consider that the calculation is pretty close to what you have in the experiment. And afterwards, we wanted to make sure that what we had imagined would work. And so we did these calculations. Yeah.
Okay, and my second question is that I see that with this kind of configuration, the possibility of flame flashing back into the channel is slightly higher. So how did you experience?
Oh, because of the diaphragm?
Because of the flame holding, possibility of flame holding in the
inside.
Inside of the channel.
It could go. Yeah. Now the orifices are small, and you blow air into this. The diaphragm could serve as a flame holder inside the. Yeah, that's a drawback. Okay. Yeah.
Okay.
All right. Yes. It didn't happen, but it's a possibility. Yes. Yeah. Yeah. All right, let's move to tell you a little bit about active control. So again, to place all that in perspective, one way to reduce the possibility of instability is to increase the losses at the boundaries. The other way is to reduce the gain of the process by working on the flames, changing the shape of the flame. So the flame shape, we've seen that different flames have different amplification characteristics. So by doing that, you can change things. You can change perhaps the phase also of the dynamical response of the flame. And so basically the idea is to work. Sometimes you can also change the resonant frequencies by modifying the geometry. That's a more complicated thing. And so the ideas here is to look at the balance equation of energy, acoustic energy, and try to see if you can reduce the gain, or if you can increase the damping, or if you can have boundaries which are more damping. And so, or include, for example, acoustic liner, something which will bring in damping. Very often, it's quite difficult. You can also plug in passive systems like quarter wave waveguides or Helmholtz resonators. So this is by increasing acoustic damping. You are above the gain here. So increased losses by inserting liners, resonator, quarter wave cavities, perforated bias flow systems. These are interesting devices. The other way is by modifying the gain. You see, trying to reduce the gain of the process. This is what we've done with the DPC. That was this idea of having flames which move up and down in different directions. You see, this is 4 million cells, 3D calculations, no flame thickening. It's a one-step Arrhenius kinetics. This is just a periodic description of these flames that we've seen I just put the same picture here again. So like that, you have the impression that you have 4 flames and not 2. It's just to impress you. So, and here you see the film, you see the flames are moving up and then they are moving down, while here you move up like that and then you move like that. And so this will be, you levelize, you make it flatter in terms of gain. So now the idea is you have the flow, combustion, acoustic feedback here. Why not include an additional loop, use a signal from the combustion process or from the pressure, send it to a controller here, use an actuator, and act on the flow and eliminate the perturbations. So this is an idea that, in fact, is very old. It's not. It has been revitalized in acoustics. People wanted to actually destroy noise by counteracting noise. So just the fact that these are waves, and if you interfere with waves, you can actually reduce them. So this is a principle that is, for example, used in headsets. When you take an airplane, you can have a reduced level of noise with certain headsets, which make it that the pressure fluctuation at your ear is essentially close to 0 by just doing active control. It's an active control device which is now available, publicly available. How effective is it? Have you used such devices? It's effective? Yes. So it reduces the level. This is based on research on these active control techniques. It's based also on the fact that you can now put controllers which are adaptive. You have an adaptation to the type of signal that is being perceived, and by suitable implementation, you can bring down. You know, the other application of such concepts is echo cancellation. You know that when you speak to a country which is very far from your own, for example, to Australia, you have a certain time lag because propagation takes a little while to go from here to Australia, and it will come back to you through the network or through the And if the delay is sufficiently long, you have a hard time speaking. When you hear your echo with a sufficient delay, it prevents you from speaking. You are unable to speak in your own reverberation. If the separation is sufficient, so that's a good device that you could use if you want somebody to stop speaking. You just put a delay, and the person will stop speaking. You won't be able to speak in its own echo. So anyway, this echo cancellation is used in telephone conversations, or used to be used. Perhaps now on the network it's not necessary, but I think this is an application of the same principles. So now, in the early days, this was proposed for rocket engines. In the early literature, for example, of Tsien and Marble and Croco and Chang, you see this possibility. They considered that you would put a sensor on the chamber, an amplifier, actuators. They would act on the fuel and oxidizer and counteract perturbations taking place in the rocket engine. And this is just a picture of my advisor, Frank Marble, and H.S. Tsien in China. They met many years later. They were very good friends. And this is a picture of them in a garden somewhere in China. So anyway, this was proposed, but was never experienced. A lot of calculations were done at the time to demonstrate that this could work, but it's already a complicated system, And first of all, the rocket engine is already quite complex. When you look at what happens around the chamber, you see turbo machinery, a lot of piping, gas generators, and a lot of things. And so it's hard to believe that you can, in addition, put something like that. But it was looked at. So more recently, in Great Britain, people started working on active control. This inspired by active control of sound. And so this group is around Cambridge, people in Cambridge. And we also started looking at that at about the same time with Thierry Poinceau. He was doing his thesis in our lab. And then we demonstrated, for example, adaptive control here. And this was finally developed into systems which could be actually included in a practical configuration. And let me show some of the setups. So for example, here you have a microphone. This is a duct. You have three injection pipes feeding non-premixed flames. A number of you have asked about the dynamics of non-premixed flames. In this case, it was a non-premixed system. And on this, we take the microphone signal and we use it to adapt the controller so that the signal that is perceived by this photomultiplier is reduced so that the heat release fluctuations are reduced. So the method is to take this signal, send it into the adaptive controller, which is optimized to reduce the microphone or the heat release. Both of them are in fact related fluctuations, and sent to an amplifier, an actuator, which acts on the fuel manifold here, and like that you can control this device. Another configuration is this one. This is more practical. You have a Moog valve, which has a fairly good bandwidth. You can modulate up to 400 hertz, and so you take the signal of the microphone, send it to this control algorithm, to the Moog valve, and you modulate the flow that goes into this injector, and the fuel is here, and what you are modulating is the airflow. And this is reported in this paper. So the system was implemented in a gas turbine. Siemens had a problem with its gas turbines. They could not reach the nominal power value because of oscillations. And so they decided to put a controller, a Moog valve on each of the burners. So all the burners were equipped with these valves, with a control system which was governing the whole thing. And there are various technical aspects to that. And they were able to operate this gas turbine, a full-size gas turbine, using active control. So in this case, this was a gas turbine, so fed with gas. So what is being modulated is actually the gas, the mass flow rate of gas. There has been a lot of theoretical work. A number of people have done theoretical work using essentially control theory ideas, transfer functions. You have to model something like that, a loop between sensor, actuator, controller, and you have on this side combustion and acoustics. So it is important to understand the combustion acoustics interaction so that you can control. So you can describe everything in terms of transfer functions. The variable S is the Laplace variable. you can actually study adaptive control, and we've done a lot of work on that. One thing which is interesting is to try to do that numerically. So perhaps I will stop here because it's 11:05. So let's stop until 11:20. Okay? So relax a little.